Okay, lesson 1.5, infinite geometric series. There's a really nice little intro in the textbook about Zeno's paradox, if you wanted to read it. It's kind of fun. And then there's also a warm-up activity with a bunch of squares that get progressively smaller and smaller. Those are not too bad to do, but I don't know if they're necessary for this unit, so you could probably move right on to the lesson. I don't think you're really going to be missing too much. So, an infinite geometric series, definition, it's a geometric series, obviously. We defined that last week, so this isn't cheating in our definition. A geometric series that has an infinite number of terms. Or another way to put that is there is no final term. There is no term at which we're going to cut it off and say, okay, what is the sum thus far? So all of our other series had ending points, which means you could always add them up. They could equal very, very big numbers, and we had a couple big ones last lesson. But this one, it can keep on going for infinity. For example, our classic example is 1 plus 2 plus 4 plus 8. This time it's just dot, dot, dot. It will literally go on forever. So the reason we're going to be talking about infinite geometric series, we didn't talk about infinite arithmetic series because arithmetic ones are always going to keep getting bigger or always going to keep getting smaller. So the sum of an infinite number of them is always going to go off to infinity, either positive infinity or negative infinity. There's no real other options here. But geometric series, that's not always the case for. It is in this one. In this one, obviously, the sums are going to keep getting bigger and bigger and bigger, and the sum of the whole series will actually be infinity. But that won't always be the case. So, convergent series. We talked about last time what a convergent series was. A convergent series has the absolute value of r less than 1. So that means the r value is something between, this is another way to write the exact same thing, it's between -1 and +1. The sign doesn't matter. So basically it's all of our negative numbers or all of our all of our decimal numbers or all of our fractions. Any of those things, as long as those fractions are less than 1, are our acceptable R values for a convergent series. So the first example of a convergent series, it goes 4 plus 2 plus 1 plus 0.5 plus 0.25, and it's going to keep on going, but the amounts you're adding on are keep getting smaller and smaller and smaller. The first thing I want us to do is actually look at this with a graph. So let's pull out our graphing calculators. You might need to pause the video while you're getting ready, but eventually you're going to go into y equals, and you're going to enter in our sum of our series formula from last lesson. So y equals 4 times 0.5 is our R value. It's halving every time. Instead of n, we're going to put x minus 1 all divided by 0.5 minus 1 inside brackets as well. So get all that into your graphing calculator. When you've got all that, then you're going to change the window. So window should be another button along the top. Change the window to read, you want your x values to be between 0 and 10, and your y values to be between 0 and 10. If you don't know how to do that, this is kind of our first time doing it, so make sure your x min says 0, your x max says 10. After that, I think it says x step or something like that. That's asking how often do you want there to be dashes on your graph. So if you put 1 for that, then you'll have a dash at 0, 1, 2, 3, 4. If you put 2 for that, it'll just be even numbers. Depends on how often you want to see dashes. 1's probably fine for this one. Sorry. So once you've changed your windows, then go hit graph on the far right, and you should end up with a graph something like this. So it starts around 4. It increases, but it keeps increasing slower and slower and slower. And this graph, this isn't necessarily the case. Sometimes there are ones shaped like this that this isn't true for, but this graph does actually have a maximum value. What I mean by that is there is a dotted line that you could draw which is above all the values this graph will ever reach. It will never actually get to that dotted line. So this will not go on for infinity. It will not keep getting bigger and bigger and bigger forever. It will actually get closer and closer to a dotted line. And we can calculate what that dotted line is. If you go to table, which I think is second graph, you can look at the table of values and you can write down a couple if you wanted to, or just scroll down and down and down. A couple I wrote down. So S of 5, the sum of the first 5 terms is 7.75. First 11 terms is 7.9961. The sum of the first 17 terms is 7.9999. And hopefully you can kind of see that we're approaching a number. If we kept getting bigger and bigger and bigger, it looks like we're going to be approaching 8. Now we don't know that yet, we don't have the formula, but it certainly looks like we're going to be approaching 8. We don't know that for sure. It could be 8.5 or 10 or something, but you would expect it to get close to that number pretty quickly. So it doesn't look like it's approaching even 8.5. It looks like it's approaching 8. That would be our guess for that one. Okay, divergent series. Let's do the same thing. So enter in this formula instead for our new divergent series. Our T1 is 4, our R is 2. And since our R is 2, there actually becomes no denominator, because 2 minus 1 just becomes 1. Dividing by 1 doesn't matter. So actually it's just this part here that you have to enter in. And once you've done that, we do need to change the window. So go into window, the x's are fine, but we're going to need the zeros to be between 0 and 1,000. And you probably want to increase the step as well so it doesn't look like a mess. Step up to like 100 or something. Once you've done all that, hit graph. You might need to pause if you're not there yet. And you should end up with some kind of a graph like that. So this one does not have a limiting value. There is no dotted line. You could say it never is going to approach. Not even a vertical one, like one over here. It will cross that eventually. It will keep going to the right and it will keep going up forever and ever and ever. There's always a bigger sum to do, and there's always a bigger value, which will be the sum. So this one goes off to infinity. So what can we say about our divergent series? Well, this is when our absolute value of r is greater than 1. So all of our r values bigger than 1. And the sums of them is either going to be infinity, or it's going to be negative infinity, or it doesn't exist as well. There's some where it doesn't exist. It could be flipping back and forth between positive and negative values, in which case you can't say it's going to equal just one of them as it goes on and on and on. It's going to constantly fluctuate between both of them. So it could be any of those options. This really, we don't care so much about the divergent series, except to make sure it isn't one. We're going to be focusing on convergent series in this unit. Okay, the formula. The formula is actually pretty straightforward and pretty easy. The sum of an infinite number of terms of a geometric series is equal to term 1. I wrote it backwards the first time. It's backwards to the other formulas, so be careful. Make sure you're reading your formula sheet correctly. It actually caught me off guard. Term 1 divided by 1 minus r this time, not r minus 1. So it is a bit backwards. This isn't too hard to derive, but you do need to know some things about kind of limits. You're letting n equal infinity, which makes some of the values disappear in some of our other formulas. I'm not going to actually derive this one. We'll save a bit of time. This sum only works if the r value is between -1 and +1, if it's convergent. So that's the only time we're going to be looking at these ones. Okay, example 1. Decide whether each of these is convergent or divergent and state the sum if it exists. So 1a is 1 minus a third plus a ninth minus, what will come after that, 1/27th. So this one, what we care about is every single term. These are kind of considered each term. Are the terms getting bigger or are they getting smaller? If they're getting smaller, then it has to be convergent, then the r value is less than 1. So this one is convergent. It is convergent, and the R value is -1/3. So -1/3 divided by 1 is -1/3. And now we need to state the sum of it. So we would say the sum of this infinite series, a series that goes on and on and on forever, is term 1 divided by 1 minus r, which is equal to 1 all over 1 minus -1/3, which is equal to 1 plus 1/3 on the bottom is 4/3, so 1 all over 4/3. And now we need to state this, but we want this as a fraction. Don't just put this in your calculator. We can do this as a fraction. This isn't beyond us. What you need to do is take this. I always find these ones a bit confusing. If you're trying to divide fractions, how do you actually draw it? I always take this biggest division symbol and I write it to the side. That's the one fraction divided by the other fraction, like this. 1 divided by is the big division, 4/3. Which then means just kiss and flip. So it's actually 1 times 3/4. So the answer is 3/4. Not too bad. That's all we have to do with that one. If you want to check your answer, you might want to actually start adding up a couple of the partial sums and see if that makes sense. Usually after a very few number of additions, like 3, 4, 5, you're already getting very, very close to where you're going to end up. Because of the way that exponential function kind of works. You get very close to it very quickly, and then you just get really, really close to it the further you go. So let's try B now. So B is 2, -4, +8. So that means B. Divergent. Like the book. B is divergent. The R value in this case is going to be -4 divided by 2 is -2. So even though it's a smaller number than the other one, it's not between -1 and +1. These terms are going to keep getting bigger and bigger and bigger, even though they're flipping signs all the time, in which case you cannot calculate the sum of the entire thing. So there is no sum. This one, actually, the sum as you go off to infinity is going to be does not exist, because it's going to constantly flip signs as the numbers get bigger and bigger and bigger. So there will be no sum for that one. So that's not too bad. We only have 2 more examples. This is a much smaller unit. Assume that each shaded square represents 1/4 of the larger square bordering the 2 adjacent sides. So this square right here, this is kind of our 1. This is 1/4 of the big square. This square right here. 2 is 1/4 of this square. 3 is 1/4 of that square. 4, and this is going to keep going on and on. I'm assuming it's infinite. It continues indefinitely. That means it's going to be infinitely long. Write the series of terms that would represent this number. The series of terms. So that means we need a set of terms which are constantly adding to each other to represent this number. So number 1 is, so the sum is equal to, we could say it's infinity. Sum as you go off to infinity is equal to 1/4. So we got this first square. But to that square we have to add square number 2. What is square number 2? Well, it's 1/4 of 1/4. So 1/4 times 1/4, it should be 1/16. If you need to kind of calculate it, you can just add up how many squares there are. 1, 2, 3, 4, 8, 12. There would be 16 that size, so yeah, it's an extra 16th. What about our number 3 here? Well, that is 1/4 of 1/16th. So 16 times 4 is 1/64th. Plus, we'll just do one more. 64 times 4 is 1/256. And it's going to keep on going on and on and on like that. That's not too bad. So how much is the total area of the square? How much of the total area of the square is shaded? So what is S of infinity in this case? Well, is it convergent? You can probably guess it is convergent. Let's actually calculate what the R is. 1/16 divided by 1/4 is 1/4. Every single time it's going to be a quarter of the original one. That means basically that number 2 is a quarter the size of number 1. So S of infinity is equal to term 1 all over 1 minus R. Did I do that right? 1 minus R, yeah. Term 1 is a quarter. You better believe I want fractions for this one. All of our things are fractions, so we got to solve this with fractions. 1 minus a quarter. Positive a quarter this time. All right, that's not too bad looking. Let's solve this with fractions. So it's equal to, I'm going to immediately pull out that divide, like we know that's coming, and on the bottom it's 1 minus a quarter is 3/4. That's basically it. Just so we understand that step, I know fractions are always a bit rough. Basically, I'm treating this big divide like the divide between two fractions. So a quarter on the numerator becomes the front. The bottom, you should be able to just kind of see 1 take away a quarter. If you had 1 pizza and you lost a quarter of your pizza, you have 3/4 left. Or you common denominator it, that's 4/4 minus 1/4 is 3/4. Okay, and then we need to kiss and flip. Equals 1/4 times 4/3. That equals, these cancel, equals 1/3. That's a nice little pleasant solution. So 1/3 of the entire square is shaded if you let these squares go off to infinity. Pretty interesting. Again, if you have questions about any of these proofs, ask me in class and I can go over them in more detail, but I'm going to keep moving on. Ooh, last page in the whole booklet. Alrighty. This one is a weird question, but once you get used to a question of this type, they shouldn't really confuse you after that, hopefully. So, this is a repeating decimal that goes on forever. Express it as an infinite geometric series. That's pretty interesting. Determine the sum of the series to express this as a fraction. So we can do two things. We can represent this as a whole bunch of numbers all being added together. And then we can actually use our formula to turn that into a single number, which represents this number, but it as a fraction instead of as a decimal. You've done kind of stuff like this. This is going to sound really difficult. It's not that bad. It's not too hard math. It's definitely not the easiest question we're going to do, but it's not too bad once you see what we're going to do. So first of all, the number we're talking about, in case you're a bit lost, is the number 0.584, 584, 584, 584, 584, and this goes on and on and on forever and ever and ever. So we want to represent this as a bunch of individual numbers all being added together. And there's different ways to look at that. The easiest way, I think probably the only way we can do this, is we're going to treat term 1 as 584 out of 1,000. So basically we were going to break these up into 3s, which makes sense. So our first 584 is out of 1,000. So then we could represent the sum of these numbers. So let's say the sum of an infinite number of numbers to represent this is 584 over 1,000. To that you have to add another 584, this time over 100,000. To that, wait, or is it a million? Let me just check how many zeros. You can always put in your calculator to check. I do want to be safe. The first one's right. 584 divided by 1, 0, 0, 0, 0, 0, 0. I think it's 6. 1, 2, 3, 4. Yes, it is 6 zeros. So every time you're adding 3 zeros. Sorry, so over a million. The next one is 584. So 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. So that represents our third block of them, and this is going to keep on going on and on and on. So all of these represents another block from our number, all being added together. And this actually is going to be a geometric series. The first one is the term that we mentioned. And what is our r in this case? So if you did this number divided by this number, just kind of picturing it, this divided by this, which means kiss and flip it, which means the 584s end up on the bottom, and they cancel. And it's 1,000 divided by a million, which is 1/1000th. So every single time you're getting 1,000 times smaller. And that should make some sense. So this is our geometric series. This is how we add up to that entire term. And now we want to represent the overall number just as a fraction. So let's use our formula. The sum of the infinite number of terms, if we wanted to add these up really quickly, we would say it's term 1 all over 1 minus r. Term 1 is 584 all over 1,000, all divided by 1 minus 1/1000th. So exact same thing. I pull out the division. And what does the bottom equal? Well, if it's 1, take away 1/1000th, it's actually everything left from a whole 1 less than 1,000th. So it's actually 999 1,000ths is what goes there. If you need to do it slowly, you're going to find a common denominator, so you're going to say it's 1,000ths over 1,000. Subtract 1 over 1,000. So that's kind of like the slow way you could do it, and then all you need to do is subtract the tops. 1,000 minus 1 is 999, and the denominator stays the same. Okay, kiss and flip. 584 all over 1,000 times 1,000 all over 999. And the only thing that happens here is the thousands cancel out each other, which makes our answer 584 all over 999. Of course, we're doing fractions, so we need to see if this reduces. Are they both even? No. Do they both divide by 3? Certainly looks like they could. This one definitely divides by 3. I tested it. This one actually does not divide by 3. So none of our even numbers will divide them. None of our powers of 3 will divide them. We could try some other numbers like 7, 21, 71, 73. But I don't think these are actually going to divide. Actually, somebody in the class let me know, because I know some of you have the fancy calculators that turn these into reduced fractions. Mine won't do that, but I think this is lowest terms. I can't be certain, but I think it is. Anyway, let's check our answer. What is that as a decimal? 584 divided by 999 is 0.584 repeated. So we did indeed get it. So we can actually go from a repeating decimal to its fraction using a sum of a geometric series, which is a weird kind of aside. I don't know how often we're going to do that, but it's a fun little challenge, and you'll probably see something like that in the homework. Okay, homework questions, and then I guess we just need to do review and get ready for the test.